Equal vectors. Welcome, everyone. Today, we are beginning a new topic in our study of vector algebra. As we progress through this unit, you will frequently encounter situations where two different-looking vectors actually represent the exact same physical quantity. Now, this might seem confusing at first. How can two different arrows in space be the same? Well, to clear up this confusion and determine if two vectors are truly identical, we use a specific mathematical concept known as equal vectors. Over the next few slides, we will define exactly what criteria must be met for this equality to exist. Definition of equal vectors. Now that we've established that we often encounter different vectors representing the same physical quantity, let's look at the formal definition of what makes them equal. When we talk about two vectors, let's call them vector A and vector B. We say they are equal, which we write as vector A equals vector B, if and only if they satisfy two specific conditions at the exact same time. First, they must have the same magnitude, which is essentially the same length. Second, they must point in the same direction. It is very important to remember that these two conditions are not optional. They must both be met. If even one of these properties is different, for instance, if they have the same length but point in different directions, or if they point the same way but have different lengths, then the vectors are not equal. As we will see in the next slide, the actual starting position of these vectors doesn't change this rule, but the magnitude and direction must remain identical. The role of position in equal vectors. Now that we have established the two fundamental requirements for equality, that both magnitude and direction must match, we need to address a very important concept, where these vectors actually sit in space. A crucial aspect of equal vectors is that their initial points, or where they begin, simply do not matter. In the context of what we call free vectors, a vector is defined solely by its magnitude and direction. It isn't tethered to a specific spot on your graph. To make this clearer, let's look at an example. Suppose we have vector A, which starts at point P and ends at point Q now. Let's look at vector B, which starts at point R and ends at point S. Even though these two vectors are located in different places on the plane, they are considered equal as long as two things are true. First, the length of the segment PQ must be equal to the length of the segment RS, and second, the line PQ must be parallel to and pointing in the same direction as the line RS. Think of it like this. If you take an arrow and slide it across a piece of paper without rotating it or stretching it, you haven't changed the vector. You've only changed its position. This leads us perfectly into our next slide, where we'll see how this concept applies to a real-world scenario involving cars on a highway. Real-world example: constant velocity. Now that we have established the formal definition and the importance of direction and magnitude, let's move away from abstract symbols and look at a real-world application to see how this works in practice. Imagine you are observing a multi-lane highway, and you see two different cars, car A and car B, driving side by side. Here is our scenario. Car A is traveling towards the east at a constant speed of 60 kilometers per hour. At the same time, car B is also traveling towards the east at a constant speed of 60 kilometers per hour. To apply our mathematical theory, let's represent the velocity of car A as vector v sub 1 and the velocity of car B as vector v sub 2. To determine if these two velocity vectors are truly equal, we need to follow the two-step verification process we discussed in the previous slide. First, let's perform step 1, compare magnitudes. We look at the speed of both vehicles. The magnitude of vector v sub 1 is 60 kilometers per hour, and the magnitude of vector v sub 2 is also 60 kilometers per hour. Since 60 equals 60, we can confirm that the magnitudes are indeed equal. Next, we move to step 2, compare directions. We observe that car A is moving towards the east and car B is also moving towards the east. Because both vectors are pointing in the exact same direction, the direction component is satisfied. Finally, we reach step 3, the conclusion. Because we have verified that both the magnitude and the direction are identical, we can mathematically conclude that vector v sub 1 equals vector v sub 2. Notice that it doesn't matter if car A is in the left lane and car B is in the right lane. As we will see in the next slide, the position or the lane they are in does not change the equality of these vectors. Common mistakes to avoid. Now, before we wrap up with our final summary, I want to pause and highlight some common pitfalls. As we've discussed in the previous slides, equality in vectors is a strict requirement, yet beginners often make a few specific errors when identifying them. First, there is the mistake of ignoring direction. It is very easy to look at two vectors, see that they have the same length, and assume they are equal. But remember our definition from slide 2, direction is just as important as magnitude. For instance, a vector of 5 units pointing north is not equal to a vector of 5 units pointing east. Even though the magnitude is the same, the direction is different, so the vectors are not equal. Second, some students make the opposite error by ignoring magnitude. They might see two vectors pointing in the same direction and assume they are identical. However, if the lengths differ, they are not equal. Take, for example, a vector of 10 units pointing north and a vector of 20 units pointing north. Because the magnitudes are different, these two vectors cannot be considered equal. Finally, a common misconception is overemphasizing position. Some students mistakenly believe that vectors must start at the exact same point to be equal. But, as we learned in slide 3 regarding free vectors, the initial point does not matter. As long as the magnitude and direction are identical, the vectors are equal, regardless of where they are located in space. Keep these distinctions in mind as we move to our final slide for the key takeaways. Key takeaways. First, let's revisit the fundamental equality condition. As we discussed earlier, for vector A to be equal to vector B, it is a two-way street. This is represented by the symbol for if and only if. Specifically, the magnitude of vector A must equal the magnitude of vector B, and the direction of vector A must be exactly the same as the direction of vector B. If you don't have both, you don't have equality. Second, remember the concept of the independence of origin. This is a point that often trips students up, but as we saw in our discussion about free vectors and the car example, the starting point, or the initial point, does not affect whether two vectors are equal. As long as the length and the direction are identical, the vectors are equal, regardless of where they are located in space. Finally, the most important requirement to keep in mind is that both conditions must be met simultaneously. As we highlighted in our common mistakes slide, satisfying only one condition, like having the same magnitude but different directions, or the same direction but different magnitudes, is simply not enough. Both magnitude and direction must be identical. All right, we have reached the end of our lesson. Let's wrap everything up by reviewing the key takeaways from today's session on equal vectors. I hope this summary helps solidify your understanding. Keep practicing, and I will see you in the next lesson.